Hello. These are 6.9 notes about inverse functions. Now today we're going to do an overview of inverse functions, and we're going to look at them and how they compare in a table, with an equation, and on a graph. As you continue your studies in mathematics, you will look more in depth into inverses, but we're gonna roll with some things here. So my first idea at the very top is the inverse of a function reverses the order of the outputs and inputs of a function. The domain of the function f gets mapped to the range of the inverse function and vice versa. So when I've got a function and the inverse function basically undoes everything the function does. So if I have a function that's saying adds 3, then the inverse function subtracts 3. If I have a function that squares something, then the inverse function square roots something. So think of inverse operations here. Okay. Whatever the range is for the original function is going to be the domain for the inverse function and vice versa. All right. So if I kind of draw this little small diagram here, the original function, okay, and then this is the notation that I use for the inverse function. This looks like f to the negative 1 power, but it's not. It's actually f inverse. So whatever I have for my domain here gets mapped to my range for the inverse, and whatever I have for the range for my original function gets mapped to my domain for my inverse. The red comment there says a function has an inverse if and only if the original function is 1-to-1. So let's talk about that for a little bit here. So a reminder that a 1-to-1 function is a function for which each item in the range corresponds to exactly one item in the domain. Oh, so many words. Okay. This is a little tougher to demonstrate because you can't see me, so this vocabulary is going to be important. When I am checking for something to be a function, is it a function? There's a variety of ways for me to check. One of those ways is called the vertical line test. So the vertical line test says that anywhere that I draw a arbitrary vertical line only touches the graph in one spot. But if I am asking the question, is it a 1-to-1 function? Then I am going to use the horizontal line test. So for example, my little left-hand diagram here, if I were to draw a horizontal line, that would not pass because that is a parabola is not 1-to-1. If I draw a horizontal line anywhere on the right-hand function, you will notice that yes, this one is a 1-to-1. So going over the vocabulary again, in order for it to be a function, it means that for each y value, I only have one x. For it to be a 1-to-1 function, it means that it is a function where each x value has only one y. So it has to go both ways. Okay. Example 1, find the inverse of the relation shown below. Graph the relation and its inverse. What is the domain and range for the function and its inverse? All right, this is a 3-part question here. The first part says find the inverse of the relation shown below. So the first thing that we're going to do is we are going to make a new table. So this table right here, it's labeled X and Y. I'm going to relabel it as X and f of X. And then I'm going to make a new table here for X and f inverse of X. So these are going to be the coordinates of my inverse function. So if I go back up to my green note there, it says that the domain of the original function gets mapped to the range of the inverse function and vice versa. So this first point right here, -3, -2, right? If I'm looking at my first coordinate, when I take the inverse of that, I get -2, -3. All right, my next coordinate is -2, 0. When I take the inverse, the X and the Y just switch. So 0, 4 becomes 4, 0, and 1, 6 becomes 6, 1. Okay, that's the first instruction for example 1. The next part of the instruction says to graph the relation and its inverse. Okay, I'm going to do my original function in red. I'm just going to try to keep this straight here. All right, and then my inverse in blue. So I'm going to graph this relation. So I'm going to go through and plot each one of these points. -3, -2. -2, 0. 0, 4, 1, 6. Now for us, graphing this, we are so used to graphing continuous functions. We need to take a beat here. These are not points that are part of a line or a different kind of function. These are just 4 points. So you may have noticed when you're reading here, one of the indicators talks about that this is the function and this is also the relation. So it is not a continuous function. I cannot connect those dots. They are just dots. They're just points. This is a non-continuous function. We also call that discrete. Okay. Yeah, that's all there is. Okay. So then we go ahead and we graph the inverse. So the inverse, remember every point for x and y just swapped. So instead of -3, -2, I have -2, -3. So I graph -2, -3, and I get this point. 0, -2, 4, 0, 6, 1. Great. So while we're talking about graphs here, let's see if I can effectively draw a line. Let's see how this goes. Yes. Okay, great. So I've got this line drawn here, and a relation or function and its inverse are symmetric about the line y equals x. So what does that mean? If we were together in person, we would be doing this on like tracing paper so you could see it. So on the screen, it's a little bit more difficult to visualize, but feel free to grab a paper and plot these points and play with it, manipulate it with your hands. If I were to concentrate on those red dots, and then I take my paper and I fold it along that green line, diagonal line that's y equals x. Hopefully you could tell that each one of these red points gets mapped to one of these blue points, right? So they are a mirror image across that line. And that is the result of having an inverse. It's always going to be true. So we will be looking at graphs and you're going to be determining, does it look like it's a reflection across that line or maybe not? It's one way to determine if a graph and its inverse are actually inverses. Okay. So the last part of this problem says, what is the domain and range for f and f inverse? Okay. We are very accustomed to choosing an interval of numbers for our domain and range. In this case, my relation is made up of 4 points. So my domain can only be the x values of those coordinates. So what are the x values in the domain? -3, -2, 0, and 1. That list is going to make up the points in my domain. Similarly for the range, the range is going to be made up of a list of these numbers. So -2, 0, 4, and 6. All right, then when I rewrite this for the f inverse, as previously discussed, the domain and the range just swap. So if I look at this table here, my domain is now -2, 0, 4, and 6, and you'll notice that that's the exact same thing as my range for my original relation. All right, and then my range is going to be -3, -2, 0, and 1. Cool. Example 2. Okay. Find the inverse of the function and graph the function and its inverse on the same coordinate plane. Okay, so we're going to do this problem two ways. We're going to do it algebraically, and then we're going to graph both functions. So you'll see the steps that are written on green on the right-hand side. This is the steps of finding the inverse algebraically. Okay, so we're going to go through these steps one at a time with this function a, f of x equals 1/2 x minus 5. Okay. We can all agree that this is a linear function. Let's find out what the inverse looks like. Step 1, rewrite f of x as y. Done. Replace f of x with y. 2, switch x and y. So I'm going to literally transpose them. Where there was a y, I'm going to write an x, and where there was an x, I'm going to write a y. Then solve for y. So remember, solving for y, I'm going to use order of operations. So to get y by itself, I'm going to add 5 first. X plus 5 is equal to 1/2 y. And then to get y by itself, I'm going to multiply by 2. So when I have 1/2 times y, we could also divide by 1/2. I tend to not divide by fractions. I'd rather multiply by the reciprocal. So I'm going to multiply the right-hand side by 2, and then I'm going to multiply the entire left-hand side by 2. So pay a little close attention there. I added in some parentheses because I have to multiply everything over there by 2. On the right-hand side, 1/2 times 2 cancels and gives me just 1y. And on the left, when I distribute this through, I have 2y plus 10. The last step in my series over here is going to be to replace y with f inverse of x. So I'm going to rewrite this. Instead of y, I'm going to write f inverse of x, and I'm going to write that first, and then the 2x plus 10. Okay, this is my inverse function. So that is part of the solution for these instructions. The other part is to graph the function and its inverse. I'm just going to rewrite this in another color to kind of use a key for my graph. Okay. So when graphing, this linear function is in slope-intercept form, so y equals mx plus b, where m is my slope, and in this case, it's my rise over run is 1/2, and b is the y-intercept, which is going to be -5. So on my table, on my coordinate plane, I have a y-intercept of -5 and a slope of up 1/2. And I get this graph way down here. Now this is a linear function. Go ahead and draw that line. This is f of x. Now when I go to draw my inverse function, I have 2x plus 10. So that's a slope of 2/1 and a y-intercept of 10. Y-intercept of 10 doesn't fit on this graph. Ugh. Okay, well, knowing that the blue function is an inverse of the red function, I can just use the coordinates of the red function to work for me. So for example, that point intercepting the y-axis, I have that 0, -5. When I map that to the inverse function, that's just -5, 0. And when I have a point like 2, -4, for my inverse function, that's just going to be -4, 2. Let's pick one more. I've got 6, -2, which will get mapped to -2, 6. Okay, so I can draw my line this way also. And you can tell that this blue line has a slope of 2, so up 2 over 1, up 2 over 1. And then it's going to intersect, kind of way up here, wherever 10 might be. Cool. This little purple note down here is just a reminder that this is a reflection over the line y equals x. So it's a bit difficult to visualize, but if you can, imagine that, we are taking this paper and folding it along this diagonal here. Cool. So below in example 3, we're going to do more finding the inverse algebraically. So we're going to move away from the graphs a little bit, and we're going to start talking about how to just kind of knock these out by using our order of operations. When we get to B and C, we've got some restrictions, and so I'm going to use Desmos to just demonstrate some things there, but we won't actually be graphing. Okay, I'm going to take my steps with me. Find the inverse of the function. All right, so I have my function, and I'm going to go through and follow my steps. So rewrite f of x as y. Okay, then switch x and y, solve for y, replace y with f inverse of x. We did this for a very similar problem in example 2, so I am going to request that you pause this and give this a chance. It's very similar to what we did in the problem just above, so go ahead and try to find the inverse on your own for example 3a. Wonderful. So hopefully you took advantage of that opportunity. The next thing I'm going to do is I'm going to swap the x and the y, and then solve for y. So to do that, I will subtract 2 first. And actually, let's go ahead and kind of relate this back to our order of operations. When I'm solving, remember I'm doing order of operations backwards. So to get y by itself, I am looking to try to add or subtract first if possible. I can subtract, so I'm going to go with that. So I subtract 2. Left with x minus 2 is equal to 4y. What can I do next? So can I divide or multiply? Yes, I can divide. So I divide the right-hand side by 4 and the left-hand side by 4. Leaving me with y is equal to x minus 2 over 4. Replace y with f inverse of x. And this is one way to write my inverse function. Now, x minus 2 divided by 4 is the same thing as 1/4 times x minus 2. And if I distribute that through, I get 1/4 x minus 1/4 times 2 is 2/4, which is a half. So either one of these is correct. Actually, I could write it like the center way up too. But the one on the right is in slope-intercept form. I believe Savas will take this written in either way. At least for the problem that I tried, it worked. But just know that there's different ways to write these problems here. Cool. All right. Now we're going to expand our understanding of inverses a little bit here, because if I have a graph that is not 1-to-1, then I cannot take its inverse. Okay. All right. So here, for my function b, f of x equals 6x squared. All right, I'm going to drag this over. And if I were to look at just this function, this is a parabola. This is not a 1-to-1 function. So if I were to take and draw a vertical line, right, it is a function, but if I draw a horizontal line, this is not 1-to-1. Therefore, I cannot find the inverse of it. So what I do to get around this so that I can find the inverse is I restrict the domain. So this is probably a very new concept, but as I look at this problem, you'll see that I have f of x equals 6x squared, comma, x is greater than or equal to 0. So I'm restricting the domain to only look at half the graph so that I can find the inverse. Okay. So let's look at what that looks like on Desmos. I have to use some different notation here. And this is not necessarily something that you need to know how to do, but it is a helpful tool to have. Let's see, is this a... There we go. So the way in Desmos that this is written is that we write the condition first, and I have to use these set brackets. So f of x is going to be, when x is greater than or equal to 0, it's going to be 6x squared. So you may notice that what happens is we just lost half of the graph. Okay, so here is what the function usually looks like for my parabola. And then we said, well, but I can't take the inverse of that, so I'm going to restrict it, and I'm only going to look at this half. And when I look at just this half of the graph, now I can take the inverse. So we're just getting a little tricky here. Okay. So now that I have this condition, I am just going to use my steps for finding the inverse algebraically. And then I will look at this condition again afterwards. Okay, so I've got my f of x equals 6x squared. I'm going to replace f of x with y, exchange the positions of x and y, and then solve. If I look at my order of operations again, is there anything to add or subtract first? Nope. Can I multiply or divide by something? Yes, I can divide. Divide by 6, divide by 6. And then can I do anything with exponents? Yes. To get y by itself, I take the square root. So I take the square root of both sides. And I'm left with y is equal to, whenever I take the square root of both sides, I get plus or minus, and then I have the square root of x divided by 6. I'm going to rewrite that with f inverse of x. And I'm going to pause because I need to go back and reconsider the greater than or equal to. All right, so when I usually graph f of x is equal to the square root of x divided by 6. Now in Desmos, I have to do this twice because I have to graph the negative also. So what you'll see on the graph now is I've got the top portion and the bottom portion, and this parabola looking thing over here that's like opening to the right is actually the positive or negative square root of x plus 6. So when I end up restricting my domain here, I get just this red function. Let me make that bolder. Okay. I just get this portion right here. Well, now this red portion is not an inverse of the green portion. So what I have to do here is when I restrict the domain for my original function, then I have to restrict the range of my inverse function. So here I have x is greater than or equal to 0. So I'm only going to be on the right-hand side. And then when I want the inverse, I'm going to restrict it and only look at the positive because now I've restricted my range to y is greater than or equal to 0. So that is that's a big idea. You might want to rewind and listen to this just another time, that little explanation. So that means when I write my final answer for this problem, I get f of x is equal to the square root of x divided by 6, only the positive one. Okay? So my last example, C here, is going to be kind of the problem in the reverse order. So now I've got a square root, and I'm going to go ahead and find the inverse. And the inverse is going to be a quadratic, but it's going to be restricted. Okay, so we're gonna play with this idea a little bit more here. So for C, I have f of x is equal to 3x plus 4, or I'm sorry, the square root of 3x plus 4. So I'm going to follow my series of steps here and replace f of x with y. I'm going to follow my order of operations. After I swap the x and the y and start solving for y. So now here when I'm doing my order of operations, it may be tempting to subtract 4 first, but I've got this square root over the whole thing, and so it kind of acts as a grouping. Well, it doesn't kind of, it actually acts as a grouping symbol. So the first thing I need to do here is I need to square both sides. And when I square the right-hand side, I get just 3y plus 4. Then I could subtract the 4, x squared minus 4 and to get y by itself, I divide by 3. So this turns into f inverse of x is equal to x squared minus 4 divided by 3, which could also be written as f inverse of x is equal to x squared, 1/3 x squared, and then minus 4/3. Both of those are correct. The one on the right is in slope-intercept form, so that is going to be probably more common to see, but they're both correct. Now with that, though, I have to restrict my domain. So all right, so if we check out the Desmos graph here for 1/3 x squared minus 4/3 and my original function. So my original function f of x is equal to the square root of 3x plus 4, and that's what I have here in green. Okay, actually, if I make this red so that it correlates with my notes, maybe that would be helpful. So this is what this function looks like. Now, when I work through it and I get my inverse function, initially I get this. I get 1/3 x squared minus 4/3, and I have this parabola. Now, those do not look like inverses of each other. My parabola, I've kind of got two sides, and then on my red function, I have just a kind of half. So what I have to do here is I have to restrict my domain. So we talked about how it's just the inverse of example B, where I'm going to have the condition where x can only be greater than or equal to 0. So if I create that condition, all right, then I get this right here. So you'll notice that, yes, these are the same graphs, but for here, I have a condition where x is greater than or equal to 0. And now, once my domain is restricted, these are symmetric about that line, y equals x. Right? Wonderful. So the last piece here is just that either way you write this, I need to have the condition that x is greater than or equal to 0. So really, if we look through this, and if you just use these steps in green to find the inverse, here's some hints for you. When given some kind of x squared function, restrict domain by using x is greater than or equal to 0. And then when given a square root of x function, restrict by only using the positive, right, and not the negative. Okay. All right. Maybe that's not very clear. Let me rewrite that, the positive. Okay, excellent. All right, and that is going to wrap it up for the 6.9 notes. These last couple of problems have got some really deep concepts in them, so it's okay to let that expand your mind and kind of play around with it a little bit. All right, thank you so much for tuning in. Bye-bye.